All right, ladies and gentlemen, we're going to go over how to do free body diagrams. Another name for a free body diagram is a force diagram. So you can consider those two terms to be interchangeable. A force diagram and a free body diagram are the same thing. Okay, so in free body diagrams or force diagrams, the diagram always shows the size and direction of forces that act on a body, and we represent that body as a point mass or a dot. The forces are indicated with arrows. The bigger the force, the longer the arrows should be. And the forces are always drawn as if they were pulls, so the arrows are always pointing away from the object. So sometimes you have to kind of slide the arrow from one side to another based on a picture, but we'll kind of see that in a minute. But the forces on force diagrams always point away from the dot. Okay, oh, this is partly done. Okay, interesting. So this is the way the forces would look that are acting on an object such as this one at the right, or excuse me, at the left. This is at rest. So if this is at rest, the normal force and the weight are balanced, and the two forces side to side, these are both static friction forces, those are balanced. So that's an object that's at rest. This could be an object that's moving at a constant velocity. But in this case, it's at rest because it has a static frictional force acting on it. This example shows we have something that is moving and accelerating to the right. We know it's accelerating to the right because this force, capital F, is larger than the kinetic friction force. So objects accelerate in the direction of the net force, so it's going to accelerate to the right. We also know it's moving because this is an FK. This is a kinetic friction force, and kinetic friction forces only operate on objects that are moving. The weight vector, W, and the normal force are balanced. So there's balanced forces in the up and down direction, unbalanced forces in the side-to-side direction, with acceleration toward the right, since the unbalanced force is toward the right. Okay, when we draw free body diagrams, we do them to determine the net forces that act on an object. And it helps you think about the direction that the forces are acting on the objects. It's always a good idea to include the positive and the directions of your frame of reference. So by convention, we usually take down to be negative and left to be negative. I won't have that marked on every one of the force diagrams we do in a moment, but that's generally the way we approach it. In this case, this would be the sum of the forces in the x direction, the side-to-side direction, would be F2 plus F4. And since F4 takes on a negative value, then this is shown as a subtraction. Then in the y direction, F3 is negative. So F1 plus F3 actually becomes F1 minus F3. Okay, let's look at this quick example. If the directions say that we have a 39,000 Newton Hummer that's driving at a constant velocity, oh, that's a gift right there, across a bridge while the motor is applying a force of 1,450 newtons. Draw the free body diagram. Because we have this indicated right here, then we know that the side-to-side forces must be balanced if it's moving at a constant velocity. And it's driving across a bridge, so we assume that bridge is flat and that the bridge supports the weight of the Hummer. So that means the up and down forces should also be balanced. So if the weight of the Hummer is 39,000 newtons, then the normal force has to be 39,000 newtons. Again, we're assuming this is a flat bridge. And if we have the motor applying this force of 1,450 newtons, then there must be a kinetic friction force in the other direction of 1,450 newtons. Otherwise, we'd have unbalanced force in this, and the car would accelerate. So over here in this side, same thing. We do the sum of the forces in the y direction, and we have 39,000 plus negative 39,000, and we get 0 newtons up and down. In the x direction, we have 1,450 newtons to the right. Add to that 1,450 newtons to the left. That takes on a negative sign, so we get 0 newtons side to side. And we know that these values have to be 0 because of this word right here. You're going to be using your critical reading skills a lot in this unit. Okay, so let's look at this whiteboard problem. If we have this particular force diagram, and these are the forces on a shopping cart in the X and Y direction, what direction would this cart accelerate? Well, it's not going to accelerate up and down because these forces are balanced. These forces side to side are unbalanced. This is the largest one, so it's going to accelerate to the right, or in the direction of the 15 Newton force. We can go through the mathematics to prove that, and we will, but it's a really quick one to see what we just said. So here are the side-to-side forces. I want to add the side-to-side forces, so this says sum of the forces, so that's why we want addition. So we're going to add the force F to the F sub k. F sub k, because that direction is negative, that's going to take on a negative sign, so in the next step, this value becomes negative. So 15 plus negative 10 means that we have a net force of negative 5, or of positive 5, and that force is in the direction of the largest force. Then up and down, we're going to add together the normal force and the weight, and we'll get 0 newtons when we do that, because down was negative, so this weight value will be a negative 10, whereas the normal force was a positive 10. So the cart is accelerating to the right. Okay, example number 2. This is the force diagram for the forces on a wagon. So sometimes when you get a little bit better at this, you'll be given details and you'll have to figure out how to build this force diagram. But right now we're just going to analyze the force diagram. So the first thing we need to do is figure out what's a reasonable frame of reference. And remember that your goal is to minimize the number of vectors that you have to resolve into perpendicular parts. So if we do an x and y frame of reference here, then the only vector that's not along the x and y path is this one right here. So this is a reasonable reference frame with up being positive and right being positive. And then that means that this is the only one that's a problem. This is the only one we have to resolve. So let's go ahead and figure out how to do that. Okay, so this is our overall force diagram. So when you are asked to build a force diagram, this is the kind of thing that you draw. In order to analyze this, we're going to create a component diagram. Don't confuse the two. Never put a component on a force diagram. The actual force applied in this case was 20 newtons at this angle, and so that's what belongs on the force diagram. Okay, so to do to resolve the value F into its parallel and perpendicular components, we have to use a triangle. So we're going to go ahead and show that we're going to isolate that 20 Newton force at the 40-degree angle. This side is the adjacent side, so this is going to be a cosine function. So F in the x direction will be 20 times cosine of 40. This side is opposite the angle, so F sub y will be 20 times the sine of 40 degrees. We could go ahead and calculate those numbers if we want to, but we don't have to. We can just carry it along as 20 sine 40 and 20 cosine 40. So that's what we're going to do. So in the next step, we're going to go through and we're going to take this force diagram and we're going to change it into a component diagram. We know now what we want those components to be because we went through this step right here. So here's what our component diagram will look like. Notice we took out this 20 Newton vector and we replaced it with these two vectors that are in blue. The force in the y direction was 20 sine 40, so it's shown in the y direction, and the force, the fx vector, is in the x direction, so it's shown in the opposite direction as this 5 Newton force. So this is a component diagram that now just requires us to do addition and subtraction to resolve it. So let's go ahead and do that. So on the next page, we'll look at how we need to go about that. So if we start with the x direction information, then we're going to use Fx, and we're going to add to Fx the friction force. Now remember, we usually call this direction negative. That's why I made this red. So that means when we drop this value in, we're adding a negative. So that's essentially what I've done here is added this negative value. And so when we do that math, we get a 10.32 newtons in the positive direction, which is going to be in the direction of this larger force. So this is to the right. Then in the y direction, we have three forces. We had the original weight vector, then we had the normal force of 8 newtons, and then we had the component of the force that was applied to at an angle. We have the y component of that stacks up here. So we have to add all three of those. This one is negative, these two are positive. So when we put this in, we end up with this, which one? This one right here is going to turn negative. So it turns out that when we do that math, that the sum of these values is 0. Well, that shouldn't be a big surprise. If you have a wagon that you're pulling along a surface, the wagon is not expected to be accelerating up and down. The wagon is in a steady position vertically with respect to the surface. It's just going to accelerate side to side or in the direction it's being pulled along the surface. So that would explain this right here. We do have a net force to the right. So this is going to accelerate to the right. Let's look a little bit, let's look at this idea a little bit about what is actually happening on this force diagram, because this is kind of interesting. Typically, when you have a force diagram where you have an object on a surface, in this case a wagon on the ground, the weight vector Fg would be balanced by the normal force. So if we didn't have this vector applied to it to pull it, then these two vectors would be the same. We would have a normal force of 21 newtons. But because this is happening at an angle, we have a component of this vector that is essentially lifting the wagon. So since the force, the F here, has a large upward component, it makes this normal force go down. The upward component of F is essentially, just as I said before, lifting the wagon, so a smaller normal force is needed to balance these forces vertically. We'll look at some problems like that, but this is the general idea that you're after there. That's kind of cool. That's a pretty cool piece of physics right there. Lots of good questions on a test related to that idea. Okay, so, oh, my dog's about to bark. Sorry about that. I hope she doesn't. So let's look at this one where we'll find the net force acting on the book. I haven't split this apart into a component diagram, so this is going to get pretty messy. This, however, is the overall force diagram. So we have a weight of 22 newtons, a normal force of 18 newtons, and a friction force of 11 newtons that is acting up the incline. So motion or impending motion of this object is down the incline. We know that because the friction force is up the incline. This may or may not be moving. We don't know that based on the information we're provided. But we do know that the friction force is always in the opposite direction of motion or impending motion. So it makes sense that this is tending to go down the incline. So let's get started on this. The net force acting on this book. Okay. So let's go ahead and resolve the weight into two components. When we look at this particular setup, this is one where it makes sense to use the parallel and perpendicular components. So this would be our perpendicular component, and this would be our parallel component. I think in this it's still going to call it x and y, where this would be y and this would be x. Okay, so if we do this math, then here's the 35-degree angle right here. It's not this one, okay? So whenever you do a force diagram like this and you break this into its parallel and perpendicular components, this angle right here translates and rotates into this one right here, coming out of the force diagram, if you've drawn this correctly. So the weight vector, the component of the weight that's acting in the perpendicular to the surface is 22 cosine of 35. So down here, this value right here, the component of the weight that acts along the incline is 22 sine 35. So if we look at the forces in the y direction, then I'm to take care of my dog. Sorry, it's probably be kind of noisy. So the y direction here is considered perpendicular to the surface. So 18 acts upward. W sub y is acting into the surface, and that value is considered negative. So the sum of the forces indicate with this negative value that they're going in the opposite directions. So whenever we do this math, we find out that those two are balanced. So that makes sense because this thing is not moving up and down relative to the surface. This is a little bit like the wagon on the surface of the wagon that we did before. So now we'll look at the values that are parallel to the surface, or in the x direction in this case. So we'll call down the incline positive, up the incline negative. So that's how this is set up. So if we take 22 sine 35 and subtract from that 11 newtons, then we find that we get a net force along the incline of 1.6 newtons, and that's acting down the incline. So this ball is going to accelerate down the incline because of the net force of 1.6 newtons acting on it. Well, that's pretty cool. Okay. So now we're going to look at what to do if we have forces in the x and y direction, and we have to solve for a resultant force or a total net force. So this should look pretty darn familiar to you from long ago whenever you started working with triangles, because this is the Pythagorean theorem. So we have one leg of a triangle, another leg of a triangle, and we're looking for the hypotenuse. So we're simply going to do a squared plus b squared equals c squared. That's all this is. A squared plus b squared equals c squared. So when we do that math, in this case, we find that the magnitude of this vector is 17.5 newtons. So that's what its magnitude is. If we want to find the angle, then we should use the inverse tangent, opposite over adjacent. So by doing the inverse tangent, 9 over 15, we find out that the angle is 31 degrees north of east. I call that above the horizontal. I think that's kind of an odd thing to say. I would call this a value of 17.5 newtons at 31 degrees above the horizontal. Okay, good job. Thank you. Lots of good stuff in that. So make sure that you're paying attention to details because you need to be really good at this. Thank you, guys.